G'day, Doug Williams here. I'm making a staircase from towers of blocks like this, and this staircase was the logo chosen for the 2023 Annual Conference of the Mathematical Association of Victoria. Good choice too for a conference with the theme Aiming High. In this workshop, what we're going to look at, using this staircase as our inspiration, is the idea that aiming high can be achieved by digging deeper. The teaching craft that we might use has already been demonstrated, at least as a starting point. There's the kinesthetic aspect of building the towers, pretty easy for kids to do in the classroom. And then there's the visual pattern that's created. And that's enough to start asking questions like, so how many blocks do we need for the next tower? Or, if I tell you that it's the 10th tower, how many blocks are needed to build it? Or if I tell you it's the 100th tower, how many blocks are needed to build it? Or, if I tell you any number for the tower, can you tell me the number of blocks to build it? And of course you can, because this pattern that's visual has a companion number pattern. And wherever there is a visual pattern, there will always be a number pattern. This visual pattern is based on the counting numbers. Tower 1, Tower 2, Tower 3, Tower 4, Tower 5, 6, 7, 8 and so on. And that number of the tower is connected to the number of blocks that is used to build the tower by the fact that it's the natural numbers. So, like a mathematician, we'll keep a record of what we're up to. In your journal, please do a quick sketch of the logo, the staircase, indicate tower number, number of blocks used to build it, calculate and record how many blocks are needed to build the 10th tower, the 100th tower. Let's see if you can write a sentence that begins, to find the number of blocks, and assuming you know the tower number, tell me what to do. And perhaps you could shortcut that sentence after you've written it into some sort of shorthand symbols. Now I'll show you my journal and see how it compares with what you've been recording so far. Okay, that was our introductory little problem. But there's more things we can ask about this staircase. For example, it might be noticed that there are horizontal cracks in the building of each tower. Obviously got a place in construction in the real world. So instead of asking the number of blocks that are needed to build a particular tower, then you might ask the number of horizontal cracks that are created in the building of that tower. So we're going to go through the same thing again. You can use your same diagram, but the questions are, When you've done that, you can start again, because there's another sort of question, or another question that relates to that, because in the building and joining there are vertical cracks as well. So the next extension, pause again for a little while, discuss, and see what you can work out and record. There's another way of identifying number patterns in our staircase stimulus. There are some special points. That point there indicates that for tower 1 we needed 1 block, and this point for tower 2 we needed 2 blocks, and for tower 3 3 blocks, and for tower 4 4 blocks, so on up to tower 5. We can identify those points with a sticker like this. And now those points provide another visual pattern, and each one of those points needs 2 numbers to identify it. The tower number and the number of blocks to build it. The tower number and the number of blocks to build it. And each of those pairs of numbers can be written as an ordered pair. In fact, it is an order. It tells you you've got to know the tower number first, and then you'll know how many blocks to use to build it. So, in your journal, there's another number pattern that can be derived from what we've just done, and that is to ask the question, so what is the change that happens from one tower to the next? The change in the number of blocks. Well, going from here, tower 1 to tower 2, the change is 1 block. And again, we can use stickers to represent that, which we'll do in a moment. And when you go from tower 2 to tower 3, the change is 1 block. And you could use stickers to indicate that. And so on for the next one. So that the finished points, the blue ones, that represent the change in what happens when you build the towers, is this function here. This is the function that connects the tower number to the number of blocks needed to build the tower. This is the function that connects the tower number with the change in the number of blocks that are used to build the tower. This function is derived from that function, and those of you who teach calculus should not be surprised to see that that is a constant. It's always 1 in this case. And are you clear about why there are 2 colours here? That point has 2 meanings. It's used in the function here, and it's used in the function there, and that was the best way that I could show you that it was used in both. Okay, make a recording of what we've just shown, show the ordered pairs, and the ordered pairs here. Make some comment for yourself about this number pattern and the number pattern derived from it, the question that was asked that led to this pattern. There's a great opportunity to include in what we're doing a little bit of mathematics from another content area in this particular problem. Let's consider turning this little staircase around this way so that it's looking at the camera differently, or vice versa. And let's just look at those first two towers. With isometric paper, explore first representing tower 1. Just tower 1. And then try representing tower 1 and 2 together. You get a representation on isometric paper that appears to be three-dimensional and picks up some of the characteristics of what you're seeing on your flat screen at the moment. An apparent three-dimensional image on a flat screen. You can go crazy if you want to and try the isometric view for our stimulus staircase, but you don't need to, because if you pick up the investigation guide that goes with this workshop at this point, there's a couple of more challenges there that suggest other things you can do with the stimulus staircase, so you might like to work on those for a while. Over to you. Don't forget to record in your journal. Digging deeper, another question we can ask based on our stimulus staircase is the total number of blocks needed to build the staircase up to any particular number of towers. So to build a staircase of 1 tower requires 1 block, but the total number to build a staircase of two towers is 3 blocks, and the total number to build a staircase of 3 towers is 6 blocks, and then 10 blocks in total, and then. Explore this in the same way as we've done before. Calculate for the 10th tower. Calculate for the 100th tower. Check your work another way. If you're confident, you should then be able to write a sentence to find the number of blocks in total and relate it to the tower number. Then you might be able to do some other things with that. You might be able to shorten the sentence in its length by using some symbols. You might be able to find some special points to graph. You might even realise that there's a reason why this number here in total is 1, this number here is 3, this number here is 6, why 1, 3, 6, 10 and 15 are called the triangle numbers. Okay, do some recording in your journal. When you come to calculate the 10th total, so all the number of blocks in order to build up to and including the 10th tower, you can probably just do an additive pattern and be patient enough to get there and you've got yourself the total. But going for the 100th requires a lot more thinking than just patiently going on for another 90 or so steps after that. And to do that, you need to realise that the only things mathematicians can really calculate are rectangles, because rectangles hold within them the concept of multiplication. So you might have to think about converting your towers, fiddling around with them to try and create a rectangle. It's not really a rectangle there, but you might be able to imagine one here. And would that be happening in all of the rest of the towers? Could you imagine a second rectangle? Or you might be able to redistribute. So if I took this block and popped it down here, oh, starting to get a rectangle down there. Ah, and wait a minute. Now I've got a rectangle. I still know this number. That hasn't changed. It's the number of the tower number. This one, though, isn't what I knew before. If I did know that, that would be an easy multiplication. And I could do a similar thing perhaps at the other end for 100. It's 3. First, second, third, fourth, fifth. Oh, the next one's the 6th. 3, half of 6. There might be something in that. Let's look back. Let's look at another example. Let's start with just 4 towers and see what happens. Can we make a rectangle? We could take that one and put it down there. Oh, that looks a bit tricky. Well, let's do some imagination. If we cut those 2 blocks through there and pick that up and popped it there, we would have a rectangle. The number of the tower would still be the same, and the count up this way on the side of the rectangle would be 2.5. So there'd be 4 lots of 2.5 used to make all of the towers up to tower 4. That would be 10. Hey, there was 10. There are 10. And hey, did that work with this? Yeah, half of the next tower. 2.5. Might be onto something there which would help us to calculate the 100th tower. Now, to investigate that completing of the rectangle that was mentioned a moment ago, I'm going to lie this staircase down flat so it's a bit more stable. There we go. Now, let's try to complete that rectangle to set up a multiplication situation so we can perhaps do some calculation. And one way to do that is to use a partner's staircase to fill in the rest of the rectangle, something like this. There we go. Now we've got 2 copies of our staircase, 2 staircases, but we've also got a rectangle, and the rectangle has the tower number as its base. So first tower, second tower, third, fourth, fifth, and the number of blocks in that tower plus 1 as its height or depth. So it's easy to do a calculation. It'll be this many times this many, but we want the result for 1 staircase, so we'd have to halve that. Now, explore that for a bit and see if how that compares with the redistribution of blocks that we did. If we get the same sort of result doing it two different ways, then there's a good chance that we've found a technique that'll work for the 100th staircase. Now, while we've got this rectangle made from the double staircases, we can notice that within it there is a square. This is a rectangle that is 5 by 6, but if I take that off, that's a square. And that square is 5 by 5. But that square is also two lots of staircases. There is the original staircase and the staircase one size smaller. Could it be that each square number is actually the sum of two staircases? That's something worth exploring. See what you get. Our two sizes of staircase that fit together to make the square give us an opportunity to look at the square from another point of view. It'll be easier to see this if I turn it into a 4 by 4 square. So let me just move some of these blocks out of the way. And there we have it. And what I'm going to suggest is that we can look further. A diagram will be easier because my hands will get in the way of the camera for a start. But we can look at a circle that fits onto this square. And that circle could be the one that fits there and goes around to touch each vertex. That might not be as useful as the one that fits there and goes around to touch at each midpoint. And that particular circle could be more useful because immediately we would know its radius, whereas that one's a bit harder to work out the radius, and that radius is half the length of the square. And we might be able to do something with that, but we'll move to a diagram to see what happens. Right, we've been exploring the total number of blocks needed to build up to and including tower such and such. Pretty easy for the first of those. It's one block to build tower 1. And there's only tower 1. But to build to tower 2 takes 3 blocks. That's those triangle numbers, number 1, number 3. And to build to tower 3 takes 6 blocks. And now we've got a relationship between the natural numbers and the triangle numbers. The triangle numbers are the sum of the natural numbers. There's only one term, there's only one answer. There's 2 terms, 1 and 2, 3 answers. There's 3 answers, 3 blocks. There's 3 terms, and so the 3 of them add to 10 blocks. And we can continue like that, building towers, and we get a very big tower. And I even have to change the camera angle so you can see the top of it. And the green blocks now are representing the function that is the sum of all of the blocks used to build up to tower such and such. I'll just move the original staircase over here so we can keep these two where we can see them. You can see these in relationship now, the original staircases and the map of how many blocks it is required to build all of the towers up to a particular one. I only need 1 block to build tower 1, so that is the point 1, 1, an ordered pair. I need 3 blocks to build 2 towers, so that is the point 2, 3. I need 6 blocks to build the 3 towers, so this is the point 3 towers needs 6 blocks, and this is the point 4 towers needs 10 blocks, and this is the point 5 towers needs 15 blocks, and it's a representation of the triangle numbers 1, 3, 6, 10, 15, which are the sum of the natural numbers, and which, when we look at these spots carefully, are not in a straight line. If I line those two up as a straight line, no, I don't think the other ones are fitting. I don't think so at all. We've chopped off some corners, and if we could get all the way down to there, we can see that we aren't getting those corners in. There's some sort of curve in this way. That curve must be governed by some sort of equation in the same way as the curve of points here were. And that curve must have some sort of derived function in the same sort as we got here, which measures the change from tower to tower. And the change from tower 1 to tower 2 is 2 blocks, so there'll be a spot there. And the change from tower 2 to tower 3 is 3 blocks, so there'll be a spot there. And the change from tower 3 to tower 4 is 4 blocks, so there'll be a spot there. And the change from tower 4 to tower 5 is 5 blocks, so there'll be a spot there. And that seems to be something we recognise. And we do know that we could then explore the change in the change. Those of us who teach calculus might just realise that when we start plotting our curve here, we've got a representation that's a pretty good estimate for the area under that curve, and it was also the representation that tends to be the starting point for refining that estimate. So that might be useful for you. Well, this is certainly proving to be a stimulating staircase. It's given us several problems to get stuck into, and I hope you've been enjoying those. But it also represents a model for doing a certain sort of proof in mathematics. The staircase or ladder proof, which has a mathematical name of mathematical induction, but let's just explore it. So let's teach this little guy to climb this staircase, and let's imagine the staircase is infinite, which is really what you've been doing when you've been writing those sentences that begin with "to find the number of." How do we teach him to climb the stairs? Well, have to get to the first step. Can you do that, mate? Sure I can, no problem. You can't get anywhere else unless you can prove that you can get to the first one for a start. From there, the process of moving is the same, whichever step you go. So, if you can assume that you got to the staircase here somewhere, the th one, meaning not quite the end, but somewhere along the way, then from there could prove that you could get up one more, then that really proves that you can go all the way, because this one where you paused could be anywhere along the way. And that's the basis of that proof called mathematical induction. Let's have a look at that in the context of that hypothesis we had about square numbers previously. That's about it for now. We've spent a lot of time together looking at this staircase, but that's the point of the workshop. Aiming high is an excellent motto to guide our teaching, but it does carry with it a sense of moving on. However, to do so may take us away from rich ground which would allow us to achieve higher aims by digging deeper. The staircase problem is an example of this sort of rich ground. It's one of the 241 problems of various depth in the Mathematics Centre task library, and 100 or so activities in calculating changes, another division of Mathematics Centre, which encourage digging deeper through primary school using a pedagogy called threading. There is no reason for maths to be taught the way it always has been. See ya!